Hello, my name is Reese McCloskey, and for my MAE ECE 535 demo, I will be exploring Lorentz forces by building and testing a speaker. Speakers convert analog signals into pressure waves that our ears process as sound. These pressure waves are created by the speaker's diaphragm. The diaphragm's movement is based on the interaction between a permanent magnet and a conductive coil carrying a time-variant current that is mimicking the analog signal. Let's talk about the components of the speaker. First off is the permanent magnet, which produces the magnetic field. Next is the enclosure, made of a foam bowl, and the spider, which supports the coil and diaphragm. My spider is made of wrapping paper because it is firm enough to support the diaphragm but yields enough to allow the coil to move. The diaphragm is also made out of a foam bowl, a material that should reduce reverberation and create a clearer sound. The coil is wrapped around a thin PVC pipe, which is glued to the bottom of the diaphragm and inserted into the hole of the spider and around the magnet. But why does this setup work? And how do we know the diaphragm is going to move up and down at all? The movement can be explained using Lorentz forces. A Lorentz force is the force on a charge of Q with a velocity v traveling through a magnetic field with a density of B. This is shown in the equation seen here, but another variation of the equation exists for current-carrying conductors in a magnetic field, where I is the current through the conductor and L is the length of the conductor. This equation is a little more useful for analyzing our speaker that utilizes a current-carrying coil and a permanent magnet producing a magnetic field through that coil. While it's a little tough to see how these two equations are related, looking at the units makes it a little clearer. Q and V have units of coulombs and meters per second, and I has units of amps, which breaks down into coulombs per second, and length has units of meters. Both scenarios leave coulombs meters per seconds to be crossed with Tesla, the units of magnetic field density. To understand the direction of the Lorentz force, we need to know about the right-hand rule. The right-hand rule says the direction of the current represented by the pointer finger placed in a magnetic field with the direction represented by the middle finger will produce a Lorentz force perpendicular to both in the direction of the thumb. So looking at our coil with the direction of the current shown in the Z direction and wanting the Lorentz force to be exerted upwards or downwards in the Y direction, we need the magnetic field lines to be perpendicular to both in the X direction. We can confirm the direction of the magnetic field lines using FEM. The mesh for my whole model and the mesh for my magnet and coil models can be seen here, and the magnetic field density plots can be seen here. Using the integration tool, we can see that there's a magnetic flux density perpendicular to the current flow in the X direction, and that a significant Lorentz force is produced in the Y direction, and a comparatively negligible force is produced in the X direction. This looks positive for the functionality of our speaker. To determine the impact of the material of the magnet, we can compare the results of two different magnet materials in FEM. The results show that neodymium magnets will produce a greater magnetic flux density and Lorentz forces on the coil, compared to ceramic magnets. This leads me to believe that the neodymium magnets will produce a louder sound, but we will confirm by testing both. Now that the speaker has been designed and assembled, we can connect the coil to a jack and plug into a computer to play some audio. To test the Lorentz force equation, we will test all of the equation's parameters, I, L, and B, with 2 levels of factor each. We will explore current by adjusting the volume output from the computer. Our speaker will connect directly to the computer using a headphone jack. Computers control the volume output by controlling the current flow through the coil of the speaker by adjusting the amplitude of the digital signal. This is similar to this potentiometer, restricting the flow of current through the coil. Conductor length will be explored using 2 different coils. One coil has 50 turns, while the other coil has 100 turns, doubling the length. And similarly to the FEM experiment, magnetic flux density will be explored using both neodymium and ceramic magnets. Testing was set up so that each combination of volume, coil, and magnet would be tested to see which configuration produced the loudest sound. The louder the sound means the greater the Lorentz force on the diaphragm. Each combination was tested using 1 kHz sine wave signal, and the decibels were measured using my phone's microphone, which was first used to measure the ambient sound level in the room. I will now play 3 seconds from each test. See if you can hear a difference. As you can see from the results table, the larger the 3 variables were, the greater the sound was. This was made clear by the setup with a neodymium magnet, 100 turns and 100% volume producing the loudest sound, and the setup with the ceramic magnet, 50 turns and 50% volume producing the lowest sound. Lorentz forces are essential to the functionality of the speaker, and it is I, L, and B that define its performance. Here are the references I used for this demo. Thank you for watching.